Good evening, everyone. Welcome. I'm so glad that you're here, and I'm so glad that you've taken part of your Tuesday night to spend with me. For those who don't know me, my name is Mark Gillette, and I'm a NASA JPL Solar System Ambassador. So as we get started, I'd like to take just a couple moments and tell you about who I am in the event that you have not attended any of my YouTube live events. I live in Central Florida, actually south of Orlando, about 15 to 20 minutes from the Walt Disney World Resort. I am a native of Central Florida, and my full-time job, I'm a professor of sociology at a local college, Valencia College in Orlando. I've been teaching sociology for over 25 years at Valencia. In addition to teaching at Valencia, I have all kinds of hobbies that keep me busy. One of my biggest hobbies is traveling. I love to travel. I've been extremely fortunate to have traveled to all 50 U.S. states. I've traveled to all 7 continents, yes, even including Antarctica. And I've traveled to roughly around 60 countries around the world. There's nothing like traveling. Like I tell my sociology students at Valencia, when I travel, not only do I get to learn a lot about other people, other cultures, other ways of thinking and doing things, I've noticed that I learn a lot about who I am as a person. And I think those comparisons are very, very important. When we don't take the time to get to know people that are different than us, if we don't read about different ideas and cultures and philosophies, if we don't kind of put ourselves out there, we don't have anything to compare what we believe to. And so I highly recommend traveling. There is nothing like it in the world. Unfortunately, with the situation that we have going on, several trips that I've had planned have been canceled, but I'm not going to complain because we are still in a bit of a crisis, and if that's the biggest problem that I have, then I think I'm going to live with it. So let's see, what else? I do want to give a shout out to some family and friends that are watching tonight. Thank you and welcome to the presentation. I also want to give a special shout out to some of the libraries around the country that have advertised and promoted my event. And so if I can take just a moment to mention some of these, we may have someone attending from the S.W. Smith Memorial Public Library in Pennsylvania, the City of Boulder in Colorado, the Technology Engagement Center, Rutherford City Library System in Tennessee, the Winfield Library in Illinois. Hello, Don. I know that you're there. We also have the Laurel Public Library in Delaware. Christian, I know that you're there as well. Thank you and welcome. We may have some people attending from the Solano County Library in California, the Cudahy Family Library in Wisconsin, the Lake Dallas Public Library in Texas. Hello, Emily. I know that you're there as well. Welcome. We may have someone attending from the Gayago Public Library in Ohio. Let's see. I think I may have a couple more here. Rachel may be attending from the Autauga Prattville Public Library in Alabama. The Moores Memorial Library in Pennsylvania, the Canal Fulton Public Library in Ohio, and the Prairie Trails Public Library in Illinois. So, I hope that I didn't miss anyone. If I did, I apologize. If you would feel comfortable doing this, I would highly appreciate it. All of you should have access to a chat box that will appear on whatever device that you're watching this on. And if you would feel comfortable doing this, if you could tell me how you heard about tonight's presentation, I would highly appreciate it. All right. So, as I mentioned earlier, I am a NASA JPL Solar System Ambassador. And that's kind of a fancy way of saying I'm a volunteer. Yes, an unpaid volunteer. I do not get paid 1 penny from NASA or JPL to do what I'm doing tonight. So you might ask, then why are you doing this? Well, I'm doing it because I really enjoy anything to do with NASA, space exploration, rockets, the universe, or anything else that it might entail. So I do want to say that I may not have answers to all of the questions that you might have, but I do encourage you at any point, if you have any questions, please feel free to type them in the chat box, and I will periodically pause, look over to my side, look at my tablet, and see if there are any questions that I can answer. So please feel free to get involved, get engaged, and get those questions asked if you'd like to do so. All right, so with that said, if you haven't subscribed to my YouTube channel as of yet, please make sure that you do and turn on notifications. And the reason that you'd like to turn on notifications is because what I periodically do is I post a very short little advertisement video that will talk about upcoming YouTube live events that I have. I generally try to have one once a month, and if you are subscribed and turn on notifications, you will see that video pop up, and then if you're interested, you can mark those on your calendar. And so here are the next two that I have coming up for the month of August. On Monday, August the 24th, starting at 7:30 p.m. Eastern Time, I'm going to be doing a presentation that I've entitled Twinkle Twinkle Little Star. Now you might think that this is geared towards children, but indeed it's not necessarily geared towards children. It's geared towards all audiences. And what I'm going to be doing, I'm going to be talking about everything that you've ever wanted to know about stars. Big stars, little stars, how stars are born, how stars die. I will be talking about our star, the sun. So I hope you can join me if you're interested and available. Monday the 24th, August 24th, starting at 7:30 p.m. Eastern Time. And for the month of September, September 30th at 7:30 p.m. Eastern Time, I will be talking about the planets. Okay, I will not only be talking about the planets in our solar system, but I will be talking about what's called exoplanets. I will be talking about exoplanets tonight a little bit, or save most of my information about exoplanets for September 30th. But simply an exoplanet is a planet that's outside of our solar system. So pretty exciting stuff. So with that said, here's our agenda for tonight. I want to talk about how we define life, talk about what's called the Drake equation, go on and talk about how are we looking for intelligent life, SETI, GAVRT, and the Very Large Array, and then we'll focus our attention on where are we looking for microbial life. We'll talk about Mars, Europa, Enceladus, and Titan, and then we'll talk about those exoplanets that I mentioned earlier, and we'll finish it up with a Q&A. On the right-hand side of your screen, you see an image that I took of the comet that you've probably heard something about, Comet Neowise. This is one 30-second exposure photo that I took. Up in the left-hand corner, you can see some dark areas. I set up my telescope very near some trees, and I ended up getting some of the leaves in the tree in that photo, but I'm pretty excited that I was able to get a relatively decent photo of that comet. Certainly not NASA quality, but it's something I took with my telescope, so I'm pretty excited about it. All right, so let's go ahead and get started with tonight's exciting presentation. Is there life beyond Earth? And so I have a very simple question before you on the screen. And that very simple yet very powerful question is, are we alone? And this is a question that human beings have been asking for many, many, many years. And I think we have all, I'm sure that every person watching this presentation has asked this question of themselves. However, I think, including myself, when we ask this question, we kind of quickly go through it and go, okay, well, maybe we are, maybe we aren't, and then we kind of dismiss it and we go about doing our other things, living our life. I'd like us to stop for just a moment and consider this. If it is discovered that life is found on, and you can fill in the blank, how does that change your thinking? So we're not talking, I guess we're talking about a hypothetical, but in this scenario that I'm painting for you, I would like you to really think about if you went to a website and you discovered that indeed NASA or some other organization unquestionably found some type of life somewhere, bang, we found it. How would that change who you are? How would that change your thinking? Okay, give that some thought. How do you suspect that this information would change other people's thinking? How would that change society's thinking? Okay, would this all be something that we would go, okay, well, we found life on Mars or Enceladus or on an exoplanet, and okay, whatever. Or is this going to make a fundamental change in our thinking? Is this going to be a revolution in our thinking as human beings living on planet Earth? So this is the deep level thinking that I really like you to give thought to as we go through tonight's presentation. Now here's some more to consider. Does it matter if the life found is intelligent or not? Does it matter if it's little green human-looking creatures or if it's simple microbial life? Okay. Now, how do we define life? And I did a lot of research for tonight's presentation, read several books, did a lot of internet research, did research through our training as a solar system ambassador, and I discovered as a social scientist that apparently biologists, astronomer, cosmologists have not come up with a standard definition of life. So what we're going to do is go with NASA's definition. And NASA, as you see on your screen, defines life broadly as a self-sustaining chemical system capable of Darwinian evolution. Okay, that's NASA's definition of life. So let's pull this definition apart. Self-sustaining. What does that mean? That means energy production. So how do living things get energy? Well, plants conduct photosynthesis. Animals and humans eat plants and animals, and that's where we get our self-sustaining system or energy from. Okay, so there's an energy component. Chemical systems, the second major component of our definition. All right, for example, humans are mostly hydrogen, oxygen, carbon, and nitrogen. Okay, so we are chemical systems. I don't think, including myself, I don't think of myself as a chemical system, but when we break our bodies down, that's exactly what we are. We are chemical systems. And the third and final major component of NASA's definition of life is Darwinian evolution, which of course refers to Charles Darwin, natural selection and reproduction, the need to reproduce the species. Okay? So, this is life as we know it. Could it be different elsewhere? Okay? Could there be silicon versus carbon-based life? Of course, we are carbon-based. Could there be some type of artificial intelligent life living somewhere in our universe? Most life on Earth is microbial. Okay? extremely small, unicellular, multicellular, etc. So on the screen in front of you, you can see that not that long ago, back in 1992, it was believed that most of the living creatures on Earth were animals. Same thing in 2011. But based on a study done just 3 years ago, you can see that the animal category has shrunk considerably. And the number one at the list is bacteria. Okay? So again, when we think about life on Earth, it's microbial life that is the best representation of what life is on planet Earth. Can we assume the same thing on other planets and celestial bodies? Well, that might be a big assumption. All right. Microorganisms are life forms too small to be viewed by the unaided eye. Extremophiles are microorganisms that live in conditions of extreme temperature, acidity, alkalinity, or chemical concentration. And so on your screen you see a picture of what's called a tardigrade. And these are microscopic organisms that are very tough and can live through just about anything. So I got a short little video that I'd like to show you about tardigrades.
Get closer. That still works.
All right, first we're going to take a look at a video. An ad, there we go. And there you go, the tardigrade. A very, very, very tough little microorganism that can withstand just about any condition that you could imagine. And this is going to become very important when we talk about some distant potentials of where life could be. All right, we cannot have a conversation about life elsewhere in the universe without talking about Frank Drake, who is an American astronomer and astrophysicist. He is perhaps best known for what's called the Drake equation. So here's the Drake equation. All right, it's used to estimate the number of communicative extraterrestrial civilizations in the Milky Way galaxy. So there's a lot of stuff going on here on the screen, but I can simplify it. All right, so we're going to start over on the left-hand side. N equals the number of civilizations in our galaxy with which communication is possible. So how do we calculate N? All right, so we start with R. R is the average rate of star formation per year in our galaxy. And according to NASA, NASA estimates a current star formation rate of between 1.5 to 3 stars per year are born. Now we multiply that times F of P. F of P is the fraction of those stars with planets. And those planets would be called exoplanets. All right? And so we have relatively recently learned that on average, every star has at least one exoplanet. Multiply that times N of E, the average number of those planets that may develop an ecosystem. All right, so in order to develop an ecosystem, you need a rocky planet like the Earth. You can't have a gas giant like Jupiter or Saturn. That's not going to work. You need to have some type of a heat source. For the Earth, one of the heat sources is, of course, the sun. And you have to have some type of an atmosphere. All right, like, for example, Mercury, the closest planet to our sun, does not have an atmosphere. All right, so there's not going to be an ecosystem, but the Earth certainly do. We have an atmosphere. All right. Now it is known, now this Drake equation that you're taking a look at was developed by Frank Drake back in the 1960s. We now know that life could actually develop on satellites or moons of planets. All right, so it doesn't have to be, it says right here, planets, but it doesn't have to be a planet. It could be a moon. We'll come back and talk about that a little bit later. All right, so now we move on. We multiply that times f of L, the fraction of those planets that succeed in developing life. And life as we know it depends on H2O, or water. We multiply that times f of I, the fraction of those planets with life that develops intelligent life. All right, so not all life is intelligent, or at least that's how we define it. Like I often like to tell my students, I think that animals are much smarter than what we give them credit for. For example, our pets, our cats and our dogs, I think they are much smarter than what we give them credit for. However, I don't think that they have developed quite the level of intelligence that we have. For example, we can send signals out into our solar system and out into the universe to try to see if there's other life out there. I'm not sure if a cat or a dog can do that, so intelligent life. We then multiply that times f of c, the fraction of those planets with intelligent life that develop interstellar communication. In other words, think about us human beings. We have not been communicating with television and radio waves that long in our history. Okay, so maybe there are living beings somewhere out there, but they have not developed a way to communicate. All right, and finally we multiply that times L, the average length of time such civilizations survive and continue to send communications. So when you consider how long it takes for information to get from, let's say, Earth to the closest stars, which would be about 4 years, that's the closest star. It takes much longer to get to other stars that are further away. And so if we're talking about stars that are millions and millions of light years away, it takes millions and millions of years if we were to send a message from Earth to get that message there. And then if they get it, if they wanted to respond back, it would take millions and millions of years to get it back. Well, will they survive that long? Okay, so that is the Drake equation. All right, I'm going to stop for a moment and see if I have any questions in the chat box. I don't see anything. I see a yay tardigrades. So yay tardigrades. All right, so the next thing I'd like to talk about is specifically, how are we looking for intelligent life? Okay, so here we're not focused on life in general. All right, non-intelligent life. We're looking specifically at intelligent life. Is there intelligent life somewhere out in our universe? And so we're going to start with the SETI Institute. The SETI Institute, or the Search for Extraterrestrial Intelligence Institute, the mission is to explore, understand, and explain the origin and nature of life in the universe and the evolution of intelligence. The Institute dates back to 1961, when Frank Drake, mentioned earlier, and other astronomers met at the Green Bank Observatory in West Virginia. In the 1970s, SETI received some funding through NASA. In 1992, a multi-million-dollar congressional funding campaign was awarded to NASA and to SETI to look for extraterrestrials. However, unfortunately, the following year in 1993, the U.S. Congress defunded the project. Now, the SETI Institute is located in Mountain View, California. It's currently a privately funded and a nonprofit scientific research institute. They are a contractor with NASA, and SETI uses radio telescopes to hunt for electromagnetic signals like radio and television waves from extraterrestrial transmitters. All right. Now keep in mind that when we send radio transmissions out into space, that they are traveling at the speed of light, and the speed of light is approximately 186,000 miles in 1 second. Even so, it can take thousands and thousands of years to reach just a few stars, and I mentioned that earlier. So I'm going to very quickly show you the SETI Institute website. I encourage you to go take a look at it when you have time, SETI.org. They have all kinds of really cool information on their website, how they go about doing what they do, outreach, education, the scientists that work for them. So SETI.org, take a look at that when you get a moment. Now I want to show you a quick little video about the SETI Allen telescope array. Basically, there was a gentleman by the name of Paul Allen, who was the co-founder of Microsoft with Bill Gates, who gave a very sizable amount of money to the SETI Institute to set up radio telescopes to do SETI work. And so I'm going to show you about 2 minutes of a tour of the Allen Array at the SETI Institute.
About that in a little while. So would you like to give us a little tour of the Allen Telescope Array?
I would switch over kind of to the phone, kind of look the audio, 1 second.
And we will say for our viewers, this is an experimental tour as far as the technology is concerned. So bear with us if the signal isn't too good.
Okay, can you hear me?
It's good.
Okay, awesome. So I guess we start outside. So today it's kind of nice and sunny. And what we see here are kind of our telescopes. So at the moment, because we have broadcast here and we're working around, we're not observing right now, but they're pointed in a direction where it kind of looks very good, similar to your background picture, just to show. But about half an hour before we started, we've done an observation where we kind of checked the instrument to see if all of the antennas, if all of the instruments, if everything works. So that was done about half an hour ago. So you can imagine those dishes are similar to the TV, the satellite dishes which you have at home, but far more sensitive. And in the center of it, what you can't really see behind that second kind of ring in the shroud is the feed, which then detects all of the signals. And all of those antennas are connected to the central signal processing room, where we receive and then kind of process all of the data.
How big are those dishes? It's difficult to get a scale.
So there's kind of, yeah.
Oh, good. We got
I guess we get a
scale.
perfect human. Yeah. So they're 6.1 meter in diameter.
Okay.
I think kind of while is finishing his thesis now, he's not doing much sports, so he's very excited.
Well, that was a good sprint. We'll see if he can run as fast back.
Yeah.
Yeah. So how many dishes are there in operation there?
So we have 42 dishes, and out of those 42 dishes, we are at the moment kind of using a subset of 10 antennas to commission a new digital signal processing backend, which I'll show you in a bit. But we are kind of have an ongoing refurbishment program and development program where we are upgrading a first generation of those feeds or the receiving part in those antennas to a new generation.
Okay, I'm going to stop it there. That's pretty exciting, though. That's what SETI uses predominantly to send radio waves out into our solar system and into the universe to see if there may be someone out there listening and who has the capability and the desire to respond, who then would send a signal back to us and it would be picked up on those radio telescopes that you just saw. All right, so that's a little bit about SETI. The next organization that I'd like to talk about that is on the quest of finding aliens or ETs out in our solar system, galaxy, or universe is the Goldstone Apple Valley Radio Telescope, GAVRT. Now, the GAVRT project is a partnership between NASA and JPL and the Lewis Center for Educational Research, which strives to inspire and enrich student learning through their active contribution to professional science. This is located just outside of Goldstone, California. The radio telescope is a decommissioned telescope from NASA. Instead of having multiple radio telescopes like we just saw at SETI, they have one, and again, it was used by NASA, but it is decommissioned. It is strictly used for educational purposes, and one of their programs that they work on at GAVRT is SETI work, the search for extraterrestrial intelligence. So I'd like to show you a short little GAVRT video that talks more about their program and working with youth on educational programs.
GAVRT is a way that students can learn about science by doing real science. So a key part of what we do with GAVRT is we want students using our big radio telescope to do science that's worthwhile and a good use of the telescope time. Teachers talk about the need for engagement, for getting the students to want to pay attention to what they're doing in class. If I walk into your classroom and say, today we're going to look for life in outer space, I've got 100% engagement. Every kid is interested.
So SETI is search for extraterrestrial intelligence, and we gather different frequencies, and then we compare that file to another one that was taken on a different date and see if any of the frequencies match up, and that could be a candidate.
We search for black holes, look for black holes, new ones that we haven't found before, so we're just collecting data for that.
We look at stars, constellations, we look at different galaxies and planets and learn new things about them.
We work with a maybe 20,000 ton telescope that is here in California, and we get to move that.
This is DSS-28, our 34-meter antenna that students use from the comfort of their classroom to look into the universe.
For a lot of the students, when they push a button in their classroom and they're watching the video of this huge radio telescope and it starts to move because they made it move, that moment is when they suddenly realize this is different. So I'm the project scientist for Juno, which is a spacecraft that's orbiting Jupiter right now. And one of the science campaigns for GAVRT is students observing Jupiter from the ground with our radio telescope. Science that they do, observing Jupiter on a day-to-day basis or a week-to-week basis over the course of years, is valuable to our mission with the Juno spacecraft at Jupiter. So in some sense, they're part of the Juno science team.
Well, GAVRT really is our flagship project. It's our partnership with NASA JPL, and we've actually just celebrated our 20th anniversary. And it's really just an opportunity for our students to partner with scientists and participate in real ongoing science work by participating in different campaigns or missions or projects with our JPL scientists.
The coolest part about it is just the fact of radio astronomy, and we're looking at objects that are so far away that they happened millions of years ago. It's coming from something that may not even exist anymore. It takes so long for that energy to come to us. So it's almost like looking into the past.
The goal is to get students working hand in hand with JPL scientists, collecting data for existing campaigns, analyzing the data, and then delivering the data, and potentially, I would be like them to use the data to support their own hypotheses and their own ideas.
The fact that we said, okay, we're going to trust you with this multi-million-dollar piece of equipment. We're going to let you do something real, and we're going to ask you to help contribute to the world, to contribute to the world's body of scientific knowledge. That whole thing, that responsibility, can change the way a kid looks at life and looks at school.
All right, so that's a pretty neat opportunity that especially students have. And I see in the chat box, Sarah J says that that's really cool. I want to do that when I'm in high school. Absolutely. Make sure that when you get to your high school, that when you go into your physics class or astronomy class, that you talk to your instructor, your teacher, about the Goldstone Apple Valley Radio Telescope, so that you get the opportunity to do what I did. I had the unique opportunity about 3 or 4 months ago to spend some time actually operating the telescope and doing a little SETI work myself. And so, with that said, I'd like to share just a couple minutes of what it was like for me to do that.
Go to the file on the Xant, down here.
Okay.
And then select galactic frame. Okay, so that brings up, let me move this over a little, picture of the Milky Way. And right here, that's this little red square, that's where we're pointing at right now. It divides that, the Milky Way up into a bunch of little tiny squares, like over 1,000 of them. And so wherever you click, it will move that red square. And then I can look on a disabled Xant over here to make sure that it's high enough in the sky for us to do. Right now, it's a pretty good time because everything's pretty high. So go ahead and just click out another spot and we'll see if it's up.
How about that?
Once you click there, so you change the number here to 786. Let me double check it and see if that's up. Okay, we're gonna have to go more on the left-hand side of center.
Okay.
Yeah.
There.
Okay, 1064. Yeah, that's good.
Okay.
All right, so go ahead and click OK,
All right.
and then click on the blue button that says track. Then click yes, we want to switch to that SETI frame. Okay, so now you can watch the antenna moving.
Okay.
Doesn't have real far to go.
Mm-hmm.
You get the spectrometer started.
I am so fortunate. I get to do some of the coolest, neatest things. And that was indeed one of the neatest things I've ever done. Had the opportunity to operate a huge radio telescope and do a little SETI work on my own. So again, if you're a young person and you're going to school, make sure that you talk to your teacher about this project so you too can do some SETI work on your own. All right, the next one I'd like to talk about is called the Carl Jansky Very Large Array, which is located in central New Mexico. It is owned and operated by the National Radio Astronomy Observatory, the NRAO. There are 27 25-meter telescopes. While a lot of observations have been on black holes, stars, and other astronomical bodies, it will soon be used for dedicated SETI, search for extraterrestrial intelligence, work. And that work will be called cosmic SETI. All right. If you are familiar with a movie that came out in 1997 called Contact, starring Jodie Foster, some of the movie was shot at this location. If you have never seen the movie Contact, Again, came out in 1997 with Jodie Foster. I cannot encourage you enough to watch it. If you're watching my presentation and you're really into the universe and planet exploration and stars and SETI work, you're definitely going to want to watch this movie. It's called Contact. It's a really, really great movie. A little old, but yet a great movie. I wanted to show you a live view, if I can get it to work, of the VLA in central, there we go, in central New Mexico. And this is a live view, live camera, live feed. My husband and I were out visiting this location back sometime last year. I think it was maybe September, October, I can't remember. And it was a great opportunity to learn a little bit more about radio astronomy. So you can go to their website and you can see the live cam, much like what I'm showing you here on this presentation. All right. So now, if you're familiar with the two gold plates that are on Voyager 1 and Voyager 2 that gives information about planet Earth, here we have an ET who grabbed one and decided to start eating it because it was confused. A little humor mixed into the mix here. Now we're going to switch gears. Where are we looking for microbial life beyond Earth? So we've been talking about where do we look for intelligent life, okay? And that's a lot of SETI work. Now we're going to talk about that small life that we would need a microscope in order to find it. Now I have little asterisks here, and that means that some possible locations of life, such as Triton, a moon of Neptune, and Pluto, a dwarf planet, may have life potential, but because of our limited time constraints, I've decided not to try to cover everything. So we're going to start with the planet Mars. And what I want to do is I'm going to come out of my PowerPoint presentation, and I am going to open up a really cool software program that I've talked about before in some of my presentations, and it's called NASA Eyes. So if you've not joined me before, I can't tell you enough about how awesome NASA Eyes are. If you've been with me before, you've probably heard me talk about it, but it's really, really neat. All you need to do is go to something like Google, type in NASA Eyes. You'll download a little bit of software on your computer, and then once you do that, you have three options: eyes on the Earth, eyes on the solar system, and eyes on exoplanets. We're going to come back to this when we talk about exoplanets a little bit later. We're going to take a look at eyes on the solar system. I'm going to go to the advanced one. It'll take just a few moments here to load. Make sure to jot this down, NASA Eyes. You're probably going to want to go back to it when we get off, when we finish up with the presentation. I see it's 8:15, and I'm probably not going to be able to finish up by 8:30, but that's okay. If you have to leave at 8:30, that is totally okay with me. All right, so here's NASA Eyes. So I'm going to scroll in just a little bit, and by scrolling in, we now see at the center of our solar system, of course, the Sun. There we have Mercury and Mercury's orbit, Venus. Here we have the Earth, and here we have Mars. So I am going to go to destinations. I'm going to go to planets. I'm going to go to Mars. And off we go. All right. Here is the planet Mars. I'm going to turn on some light so we can see it. And here you have a great opportunity to completely manipulate the screen and take a look at the North Pole, the South Pole. You can also see, for example, where the InSight lander is currently at, Curiosity Rover. All right, I'll be talking about both of those a little bit later. By the way, there's going to be a very important launch in 2 days. I will be talking about that as well. The Perseverance rover, Mars 2020, will be launching on Thursday. The The landing site, I believe, for that will be somewhere around in here, the Jezero crater. We'll come back to that a little bit later. But this NASA EYES is really cool because it gives you all kinds of information about Mars. And I'm not going to go through it right now, but I'm going to encourage you to, on your own time, go to NASA EYES and take a look at this, and you can see all kinds of really cool information about all this stuff that we're going to be talking about. So we're going to go back to my presentation. All right. So Mars is the fourth planet from our star, the Sun. The current distance from Earth to Mars is roughly about 39 million miles. It is believed that at one point Mars had a much thicker atmosphere than what it currently has. It has a very thin atmosphere as compared to the Earth. It is believed that a very, very long time ago, Mars was much warmer than what it is today. Today, the average temperature is below freezing on Mars. There are high levels of ultraviolet radiation today that come from the sun, which breaks down organic molecules. We have not found any living creatures or things on the surface, the Martian surface, but it is believed that if we start digging down into the Martian surface, that is our best chance of finding anything that is either currently alive or a fossil, something that has lived a long time ago in the past. Okay, so digging will be very important of our exploration of microbial life on Mars. If life existed or currently exists, it's below the Martian surface. All right. Water ice is also below the surface and also visible on the surface of the North Pole. And so if we look at the North Pole, well, I'm not going to go back to the NASA EYES. You can see down here, here's some polar ice. All right. So, could existing or past life on Mars originally be from Earth? If you do research on where life comes from, there are many hypotheses that says that we human beings could actually be Martians. Okay? Our life started on Mars. We hitched a ride on something like an asteroid or a comet, microbial life we're talking about here, not human beings, and eventually came to Earth. All right, and started the Darwinian process. Or vice versa. If we find life on Mars, the opposite could have happened. So if we find life, past or current, on Mars, the big question will then be, is it because it came from somewhere else, or is it what we call a second genesis, a completely separate start to life, separate from the Earth? Okay? All right. I want to talk about what's happening right now. I showed you the landing spots for both the Mars InSight lander and the Mars Curiosity rover. The Mars Curiosity rover landed on Mars in August of 2012. It is a rover, has wheels, moves around. It has gone about 14 miles on the Martian surface. The lander on the left-hand side, the Mars InSight lander, landed on Mars in November of 2018. You can see that there are no wheels, so it doesn't move around. It is steady in one location. You can see this is a drill. The ultimate goal is to drill hopefully down to, 16 feet into the surface, I believe. That's the ultimate goal, and to see what's going on below the surface, because again, keep in mind, there's so much radiation because of the lack of atmosphere around Mars that if anything was living on the surface, it would quickly die due to the radiation. So if anything's living, it has to be protected, and hopefully that Martian surface, the land, will help to protect anything that might be alive. All right, so I did mention this earlier, but it certainly is worth repeating. NASA's newest Mars rover, the Perseverance, originally called Mars 2020, is scheduled to be launched from Cape Canaveral 2 days from now, July the 30th. I believe it is currently scheduled for 7:32 a.m. Eastern Time. I am very fortunate to live in Central Florida, and one of the benefits is if it's clear, I can walk outside my door, look to the east, and I can see the rockets going off. So I'm hoping for clear weather on Thursday morning, and I'm going to go out and see if I can capture a little video, and if I can, or put it on my YouTube channel, and if you'd like to, come back and enjoy any video that I might be able to capture. On the right-hand side of your screen, you see Ingenuity. Ingenuity is NASA's first helicopter that's going to fly on another world. And so it is attached to the bottom of the Mars rover on the left-hand side, Perseverance. And so when Perseverance lands on Mars, scheduled for February 18th, 2021, so it's going to take about 6.5 months to get to Mars, that helicopter is going to separate on descent and then hopefully will fly around. So be paying attention to the news in February to see if they were able to actually pull this off. Okay, so here's a image from NASA of where Curiosity is currently on Mars, where InSight is, and there's where Perseverance is headed to, the Jezero crater on Mars. Just incredible stuff. It's just so exciting to think that how much work and engineering and thought goes into creating these instruments that we then put on rockets and we shoot into space, and they have to be at the right time and the right orbit at the right speed to land at the right place. Incredible amount of work that goes into something like this. And you know, we humans can do such awesome, wonderful things when we come together and work together to do these things. Unfortunately, as I tell my sociology students, we spend so much time, I'm becoming a little preachy here, so much time judging one another and thinking I'm better than you and we're better than you and we know something you don't know, and it hinders our ability to do great and awesome and wonderful things. And if we humans could get over this silliness and work together, we could accomplish such awesome, wonderful things. And that is my hope, that one day we will be able to do that. All right, let's move on to a different world. We're moved from from Mars to Europa. Europa is a moon of Jupiter. So I want to go back to the eyes that I mentioned earlier. We're going to go to Jupiter here. Let's see here, and I'm going to find Europa. Europa is one of the Galatian moons, one of the 4 Galatian moons of Jupiter. So we're going to go ahead and zoom right over to Europa. So here's Europa, again, with eyes. You can spell around it. Let's see if I can find Jupiter here by kind of scooting around the screen. I think I find, there we go. There's the planet Jupiter. Jupiter is the biggest planet in our solar system. So what's the significance of Europa? All right, well, the temperature rarely exceeds minus 260 degrees Fahrenheit. So it's really, really, really cold. There are fractured, icy shell blankets of ice on the moon. So basically what you're looking at here is frozen water or ice. There are giant geysers that occasionally blast water vapor about 125 miles above the surface of Europa. Now, Europa receives very intense radiation from its host star. From its host planet, Jupiter. So anything that would live on the surface because of that radiation, if it could live on the surface, would not last very long. So where would there be microbial life on this on this moon, if there is any. It would be under the frozen ice. Okay? It is believed that the subsurface ocean of Europa has twice the volume of all of the oceans on planet Earth. So there is a whole lot of water that is on this moon. And who would think? You know, not that long ago, astrophysicists and astronomers and cosmologists thought that moons were just boring dead things that may look pretty and are exciting to take pictures of, to image. But now we believe that they are much, much more than what we ever could imagine them to be, and they are a real potential for hosting life. Okay? Now, it is too far from the sun, about 485 million miles, to receive enough heat to keep the oceans liquid. But it has its own heat source, Jupiter, that big planet right there. When orbiting it, it is squeezed and squished. This friction heats up the moon's solid interior, and this is called tidal heating. All of this, it is believed, creates volcanoes and hydrothermal vents on the ocean floor. Okay? So there is heat, is believed, below these oceans, and heat is energy. And energy is needed for life to exist. So it has all of the ingredients that is needed for life as we know it on this moon. The question is it there? It's going to be really, really difficult for us to determine that, because the only way we can determine it is to send something there and start drilling down deep, deep, deep within that ice. Sending some type of a miniature submarine or something with a camera that can get down in there and take a look at what's going on by those hydrothermal vents that we believe that are down there. See, on planet Earth, in our deep oceans, there are hydrothermal vents. And there are many creatures that live down there, like those extreme creatures. I'm not recalling their name. The extremophiles. And so if extremophiles can live on planet Earth, we believe that extremophiles could also live on this particular moon. All right. Let's go back to my presentation here. I want to show you a little bit about the NASA's Europa Clipper mission.
Europa is the most likely place to find life in our solar system today because we think there's a liquid water ocean beneath its surface. Now we know that on Earth, everywhere that there's water, we find life. So could Europa have the ingredients to support life?
We might be actually looking at a body that is presently alive, presently active, and presently undergoing its geology. There is too much evidence right now lying around on the surface, the red stuff, that suggests that something's going on there. Is that an environment that is habitable for any sort of life form? By golly, we really have got to go back and figure that out.
We have designed the Europa mission to take a spacecraft and its set of instruments all the way from planet Earth to Jupiter.
Previous mission concepts were for a spacecraft that would orbit Europa, but Europa is bathed in radiation from Jupiter. Any mission that goes in the vicinity of Europa is cooked pretty quickly. Instead, we're looking at a mission that will orbit Jupiter, make close flybys of Europa, and then zip out of the high radiation region.
Kind of like when I was a kid, we had the sprinklers, and we didn't want to be too close to the sprinkler head, so we would run in and get a little water and then run back out again.
This allows us to have a mission that's many years long and to collect and transmit lots and lots of data. As Europa orbits Jupiter, it flexes and we could measure the gravitational change of Europa by encountering Europa at different points in its orbit. On a typical flyby, we would turn on our remote sensing instruments, we would image the surface, we would interrogate the surface with spectroscopy, and we would do the same thing on the way out. And we would essentially rinse and repeat and do this many, many times until we understand Europa globally. Images from the Hubble Space Telescope tells us that Europa might be erupting plumes of water high into space. If that's true, then we could fly through those plumes with a spacecraft and literally taste it to understand the composition of Europa's interior.
If it does have the ability to harbor life, how does that work exactly? We'll have enough instrumentation to really pinpoint exactly how the mechanisms would work for replenishing the nutrients in a subsurface ocean.
Europa is so important because we want to understand, are we alone in the cosmos? If there's life in Europa, it almost certainly was completely independent from the origin of life on Earth. That would mean the origin of life must be pretty easy throughout the galaxy and beyond.
Okay, I'm going to pause for a moment. I see a couple questions in the chat box. I see a question from Sean. How does the Mars helicopter differ from an earthly helicopter? Well, the Mars helicopter that was developed and manufactured by JPL is extremely small. But I would say the biggest difference that I'm aware of is that it was engineered to be able to fly in Mars's extremely thin atmosphere. In other words, there's not much out there for the wings to kind of catch on to. And so the speed of the propellers and the amount of atmosphere that it can capture is needed in order to keep it up in the air. And so that was, from my understanding, one of the biggest differences between an Earth-bound helicopter and the Mars-bound, because of the difference in the atmosphere. There are even concerns that the helicopter being sent to Mars may not be able to fly because the atmosphere is just so incredibly thin. And I see a question here from A. Kopin. How thick is the ice? And I believe we're talking here about Europa. I don't have an exact depth, but I do know that the ice is miles and miles and miles deep. All right, I do know that to be the case. Okay, let's go on to another moon. I see that I'm already past my time, so if you have to go, no problem. Come back and see the rest of this video when you have time. If you'd like to stick with me, please do so. I'm going to keep going. We're going to go on to the moon of Enceladus. This is a moon now of Saturn, and I'd like to go back to our NASA eyes, and we're going to go to Saturn, and we're going to go to right here to Enceladus, and off we go. All right, so here's Enceladus, Saturn's sixth largest moon. It has massive plumes of water vapor that are coming from 4 fissures, which are called tiger stripes on the South Pole. And here you go. Here they are right there. So you can see with this NASA eyes, it's really cool. All right. It is believed also that this moon, Enceladus, has a subsurface ocean, much like what we were talking about with Enceladus around Jupiter. It is also believed that there are hydrothermal vents on the sea floor. So again, there you go. You've got an energy source and you've got the right temperature. And so there's a possibility that there may be some type of microbial life that lives on this moon. And going back to my original question I asked, if we find life, how does that change you and me and society? Well, does it matter if it's intelligent life, or does it matter if it's very small microbial life that we need a microscope to look at? To me, it doesn't matter. Finding life on Enceladus or Europa it would change everything. It would just totally change, I believe, how we humans would look at the world. So let me see if I can pull up Saturn here. I should be able to find Saturn. There she is. There's the planet Saturn. All right. So that's our NASA eyes again. Going back here to the presentation. All right. And so I want to take a look at a quick little video about the Cassini, Enceladus and Cassini. And Cassini was a mission, a NASA mission that explored Saturn. Wait a minute. So this is the NASA website, and this will give you lots of information about this moon, Enceladus. For example, it's an icy moon. Its diameter is about 313 miles. Each day is about 33 hours. All right, let me go back to what I was trying to get at here. Here's what I'm trying to get at.
In February 2005, we had our first close flyby of Enceladus, and the magnetometer signal saw something unusual. What a magnetometer does is it measures the magnetic field in the vicinity of the instrument. We had a look at the wiggles, and they looked strange. The magnetic field of Saturn is moving towards it, and it couldn't penetrate down onto the surface, which was pointing to an atmospheric signature of some kind. Here it looked like it had a tiny atmosphere. In March, we came even closer, looking for that same strange signal. What it showed was that the signature, the atmospheric signature we were seeing, was focused at the South Pole. It was almost like there was a cometary plume of water vapor coming off of the South Pole. People were saying, it's gotta be jets, it's gotta be jets. And the imaging team was saying, no, we don't want to say that, until we're sure. So we went closer. We came within 175 kilometers of Enceladus. Then we got the data back, and it was spectacular. And then we found the evidence. Geysers coming out of the South Pole with water vapor and water ice particles. They were active geysers at the South Pole of Enceladus. Because we were so close, all of the other instruments were able to take really good data. And we put together all of this data. We saw the cracks, the tiger stripes at the South Pole. We saw heat leaking out from these tiger stripes. On subsequent flybys, we found organic material, dust, water vapor coming out of the plume. The Cassini discoveries in the first 3 flybys were so amazing, we changed our focus and added 20 more flybys of Enceladus, including 7 through the icy jets. The surprising magnetometer reading led us to the liquid water ocean underneath Enceladus's icy crust. After over a decade of research with Cassini, we now know there's a potential for the ocean on Enceladus to support life. And that has altered the way we think about where life might be found in our own solar system and in the worlds beyond.
All right, so the NASA Cassini mission officially ended on September 15th, 2017. And NASA has a proposed mission to go specifically to Saturn's moon Enceladus, and they currently are calling it ELF, Enceladus Life Finder. One more moon I'd like to talk about tonight, and that's Titan, another moon of Saturn. I'm going to skip the NASA overview of Titan. You can go to nasa.gov and find out all kinds of information about all of our planets and the moons around those planets. So here's some information about Titan. It is the largest moon of Saturn. It rains. It rains on Titan. But it's not raining liquid water like here on Earth. It's raining liquid methane and hydrocarbons. And if you combine these to form complex compounds, these are the raw ingredients of life All right. So no other place, no other world that we are aware of other than Earth where it rains and has a rain cycle that feeds lakes and rivers. This is a pretty neat moon, Titan. It is the second densest atmosphere other than the planet Venus in our solar system. The average temperature is roughly about 290 degrees below zero Fahrenheit. Titan's largest sea is roughly 5 times the size of Lake Superior. It is believed that there is a subsurface ocean 60 miles beneath the ice surface, and it might have hydrothermal vents. So you're seeing this pattern of ice, and below the ice there's a subsurface ocean, and the ocean is somehow heated by some type of internal activity. All right. The European Space Agency's ESA's Huygens probe lasted 90 minutes after landing on Titan's surface on January 14th, 2005. And so I would like to show you the actual video footage of this probe landing on Titan. This is the actual footage. Well, what you're looking at now is not the actual footage. This is artist's rendition of what they believe it would look like. This is the actual footage of it landing. Isn't that cool? I'm going to stop for a moment. I see a couple questions in the chat box. Hi, Kathy. I don't know if this makes sense, but you mentioned that this one is labeled an icy moon. What other types of moons are there? So yes, there are other types of moons. For example, our moon. Our moon is not an icy moon. It has some ice on it, specifically at the South Pole, and when we return to the moon in 2024 with the Artemis program, that is our destination. Yeah, so there are different types of moons. And then there's a question from Sean about, is Enceladus tidally locked to Jupiter? And I don't know. I'm sorry, I don't know. I should probably know that, but I do not know. I'd have to look that up. All right, and so I'm really going over my time, but I do want to mention exoplanets. And I really want to go back to my NASA eyes here and show you the stuff that you can see about exoplanets. Now it takes a little bit more time to load the exoplanet video, so bear with me. Let's see here, exoplanets. So again, when we get off, don't forget to go to NASA Eyes. Look it up in Google, download the software, and you can just spend hours and hours and hours looking at everything in our solar system, the Earth. You can look at exoplanets, much like what we're going to do now. I'll go ahead and talk about exoplanets while this is loading. Again, an exoplanet is simply a planet outside of our solar system. It is now believed that on average, every star has at least one planet. All right, probably a lot more. I'm going to go full screen. There we go.
You are now 1,000 light years from Earth, looking at all the stars where planets have been discovered. Our sun is at the center. Our galaxy is home to more than 1 billion stars. The stars you see represent only a tiny fraction of those. Click and drag with your mouse to explore our galactic neighborhood and search for planets that might be hospitable to life.
So I want to show you a couple things here. Back in 2017, NASA's Spitzer Space Telescope revealed this system called the TRAPPIST system. And so I'm going to turn it sideways. I'm going to kind of scroll in a little bit so you can take a look at it. And so here is a star system with multiple planets, and it has Earth-sized planets, and it's in the habitable zone. In a moment, I'll talk about the habitable zone. And let's see, there was one other thing I'd like to show you here, and it's not going to let me do it. All right. Well, I do encourage you to take some time and explore the eyes on exoplanets. All right. Now, I'm going to be doing a presentation on planets, and it's going to include talking about exoplanets, as I mentioned at the very beginning of tonight's presentation. That's going to be on Wednesday, September 30th, starting at 7:30 p.m. Eastern Time. So I'm going to very quickly go through a little information about exoplanets, so come back and see me on September 30th if you'd like to hear more about exoplanets. Here you see on your screen what's called the habitable zone. And here we have our sun. And so you could replace our sun with any star, and based on the size of that star, based on the energy that it puts out, there's going to be a certain zone called the habitable zone, which means that if it got any closer, if a planet got closer to the star, the water on the planet would evaporate. If the planet was further away than the habitable zone, the water would freeze. Therefore, when a planet is in that star's habitable zone, there is liquid water. Okay? It was once thought that life could only exist in the habitable zone. As, however, I mentioned earlier, we now know that other planetary bodies, such as moons, under the right conditions, could harbor life. This is what's called the transit approach of understanding and discovering other planets out in the solar system. And so here is a planet, and as it goes in front of its star, it's going to block out a certain percentage of the light being emitted from the star. And so here you can see the dip in the amount of light that's being put out from that star. And with scientific analysis, we can then determine without even seeing the exoplanet that there's an exoplanet there. That's one of several ways we can determine if there is an exoplanet going around a star. There are other systems such as a wobble effect, and I'm not going to go into that right now. This is probably the most popular method of discovering exoplanets. It's based on transits. NASA had a space telescope called the Kepler Space Telescope from 2009 to 2018, and you can see that it discovered a whole bunch of potential candidates for exoplanets. Okay, and this is kind of ranking them. There's also another NASA satellite. It's called the TESS, the Transiting Exoplanet Survey Satellite. The mission started only a couple years ago in 2018, and SETI has a video that talks about an Earth-like planet that was found in the habitable zone based on the research of this NASA Space Telescope, TESS.
Hi, Seth Shostak here, astronomer at the SETI Institute. Well, it's 2020. I'm not talking about my vision, which is not 2020, but I'm talking about, well, a new year. And we already have some interesting results from the TESS instrument. TESS, T-E-S-S, stands for Transiting Exoplanet Survey Satellite, but it's a lot easier to say TESS. Now, TESS has been up there for about a year and a half, trying to find planets sort of the size of the Earth around nearby stars. And you may say, well, why? And the answer to that is, if they're nearby and they're kind of like the Earth, they're not only interesting, I mean, they might have life, but also they're close enough that follow-up observations can be made with other telescopes to try and find out whether these planets really have things like atmospheres and oceans and so forth. Well, last week in Honolulu at the American Astronomical Society meeting, there was an announcement that TESS has found its first, more or less, Earth-sized planet around a star and is in the habitable zone. Now, what's the habitable zone? Now, you're probably thinking, I don't know, the suburbs? What's the habitable zone? No, the habitable zone is that distance from the star where you could have liquid oceans that are neither frozen all the time or boiling all the time. Okay, so they found this thing around a star, which is about 100 light years away. The name of the star, TOI 700. Really rolls off the tongue. Now, what does that mean, TOI? TESS Object of Interest, kind of understated. So, TESS Object of Interest 700, that star, it turns out it had been misclassified. It's actually a kind of a runty little star, what's called a red dwarf. So, it's, you know, it's only maybe 70–80% the size of the sun, and it's only about half the temperature. So, if you were on the surface of that star, not that I recommend that, it would be kind of the melting point of molybdenum, right? That's more or less the temperature. But this planet is pretty close to the star. It orbits every 37 days, something like that. And being so close, it gets more of the star's output, and the temperatures there are probably comparable to what you have in your own hometown. So they found this planet. It's only slightly larger than Earth, maybe 20% larger than the Earth. The right temperature around a star 100 light years. All right, what are we going to do? Well, there'll be follow-up observations surely in the next decade, maybe much sooner, to try and see if there's an atmosphere or something like that there. But it is kind of exciting. One last thing, don't book your ticket to go to TOI 700D, as this planet is named, because being 100 light years away means it's going to take you about 2 million years in a rocket ship to get there. That's a little bit long.
Okay. And that's the famous Seth from the SETI Institute. Couple more things about exoplanets. To date, there are now about 4,000 known exoplanets. Keep in mind that up until about the mid-1990s, we didn't even know for sure that there were any exoplanets at all. All right, so we've moved a long way in a very short period of time. Let me read this to you. Microbes are far too small to photograph from space, so scientists look for big for biosignatures, the presence of elements or compounds associated with life. Okay? Spectroscopy is the analysis of light energy reflected by planets or stars. By reading this reflected light, scientists can determine elements and compounds in the atmosphere. This indicates whether a planet has a potential host, is a potential host for life. So you think about how far away these stars are, much like what Seth just talked about. It's incredible, you know, millions of light years away in some cases. So how could we possibly even start to determine if there's life there? Well, it's based on this spectroscopy. And so I'm not going to go into a lot of detail about this, but here's the what's called the electromagnetic spectrum. And this is the visible part of it right here. And then you have X-rays, and you have infrared, microwaves, and radio. And so what happens is the star is sending out light, and if the planet around, the exoplanet around the star has an atmosphere, that light will go through the atmosphere. And based on that, we can then see what's in the atmosphere: sodium, hydrogen, calcium, mercury, or any other of the elements that might be found in an atmosphere. And if there are certain elements found in the atmosphere that would lead us to think, hey, there might be life there, like, you know, hydrogen, oxygen, carbon dioxide, then that might be a candidate for life, a potential exoplanet that has some of the components that we know are necessary to host life. All right, well, I have spent a lot of time, much longer than I thought I would, on talking about some of these exciting topics, but I really like them, and I hope that you enjoyed them as well. Before we part ways, I do want to remind you to please come back and see me next month on Monday, August the 24th at 7:30 p.m. Eastern Time, when I'm going to be sharing all the information that I can tell you about stars. If you haven't subscribed, please do so. Turn on those notifications so that you know when I'm posting those short promo videos about my upcoming events. I'm looking in the chat box and I don't see any additional questions coming up. I do highly appreciate your questions. I don't always have the answers to them, but I do the very best job that I can. So if anyone has any questions, if you can pop them in the box real quick for me, I'll be glad to address them. Other than that, I'm not seeing anything. I do highly appreciate all of you again spending part of your Tuesday evening with me, and with no questions. Oh, wait a minute. No, thank you. Age 8, isn't that awesome? Thank you. Well, I thank you for attending, and I do hope to see you very soon again for another YouTube Live event from me, Mark Gillette, NASA JPL Solar System Ambassador. Thank you so much for joining me, and have a wonderful rest of your evening. Bye-bye.